I am Seema, student of BSc Chemistry Honors final year. This video is especially for the visually impaired students. This chapter is the organic chemistry, fats, oils and the detergents. Introductions. Oils and the fats are widely distributed in the nature, both in the animal and the plant kingdoms. In animals, they are present under the skin and in the muscles, but in the plants, they are mainly found in the seeds. Some important examples of the fats are the butter, lard, tallow, beef, etc. While the groundnut oil, cottonseed oil, olive oil, palm oil, coconut oil, sunflower oil, soybean oil, linseed oil, sesame oils, etc. are important examples of the vegetable oil. Fat and the oils are the one of the three major constituents of our food. The other two being carbohydrates and the proteins. In fact, fats and oils serve as the energy reservoirs for the animals. In the human beings, only a few hundred grams of the glycogen carbohydrate can be stored, which can barely supply the body energy need for about the 12 to 18 hours. In contrast, large amount of the fats, 12 kg for an average person weighing 70 kg, can be stored with which can supply the body energy needs for about 8 weeks. Besides these, oils and fats serve as raw material for a number of the industrial such as soap, paints, varnishes and vanaspati ghee. Natural fats. The fats obtained from the animal sources such as the butter from the milk of the cows and buffaloes, lard from the hogs and tallows from the sheep coats, etc. are called natural fats. This name is simply given to the differentiate these fats from those fats which are obtained by the hydrogenation of the oil. Edible and the non-edible oil. Oils such as the groundnut oil, sunflower oil, soybean oil, mustard oil, olive oil, sesame oil, which are used for cooking the purposes, are called edible oil, while the oils such as the cottonseed oil, castor seed oil, and the mahua oil, which are used in the soap, paints, varnishes industries, are called the non-edible or industrial oil. On this basis, iodine value oils have also been classified as drying, semi-drying, or non-drying oil. Industrial oil may include the essential oil or the mineral oil. Essential oils are mainly used in the perfumes, cosmetics, and in the pharmaceutical products. On the other hand, mineral oil such as the paraffin oil is a mixture of the saturated and the unsaturated hydrocarbons and not esters or triglycerides. They cannot be saponified. They are also called oily simply because of their physical appearance. They are non-edible and are mainly used as the fuels. Triglycerides composition of the oils and the fats. As stated above, fats and oils are triesters of the glycerol with the higher aliphatic monocarboxylic acids, fatty acids. In the other words, they are triglycerols and are commonly known as the glycerides. Fatty acids. With only a few exceptions, all the monocarboxylic acids isolated from fats and oils are straight-chain compounds containing the 3 to 18 carbon atoms. Further, with the exceptions of only C3 and C5 acids, all other acids found in the fats and oil contain the even number of the carbon atoms. The chief saturated fatty acids present in the oils and the fats. Besides the saturated fatty acids, unsaturated fatty acids containing the one or more the double bonds in the cis orientations may also be present in the oils and the fats. The chief unsaturated fatty acids present in the oils and the fats are classifications of the glycerides. The three fatty acids in the glycerides may be classified same or different. Therefore, glycerides are classified as simple or mixed glycerides according as they have the same or the different acids residues. For example, glycerides are further classified into the saturated and the unsaturated glycerides according as they contain the saturated fatty acids residues or unsaturated fatty acids residues. For example, the triolone. Both simple and the mixed glycerides are found in the natural oils and the fats. In fact, oils and the fats are the complex mixtures of the mixed glycerides along with the small amount of the simple glycerides. Chemical difference between the oils and fats. The main difference between the oils and fats in the proportion of saturated and unsaturated glycerides. Triglycerides with the higher proportions of saturated acid residues such as the palmitic acids, stearic acids, are the solids at the ordinary temperature and are called fats, while those with the higher proportions of the unsaturated acid residues, such as the oleic acids, linoleic acid, etc., are the lipids at the ordinary temperature and are called the oils. Melting points of the glycerides. As stated above, fatty acids have one or more the double bonds having the less stable cis stereochemistry. For example, oleic acid has the one cis double bonds at the C9, linoleic acid C17 S31COH has the two double bonds and the C9 and C12, while the linoleic acid C17 S21C H29COH has the three cis double bonds at the C9, C12 and the C15 positions. These cis double bonds have the vital biological importance in the solid state. The molecules of the saturated fatty acids fit closely in the crystal lattice due to their zigzag tetrahedral structure. On the other hand, cis unsaturated fatty acids have a band at the double bond and hence do not fit the closely, thereby lowering the melting point's chemical properties. Fats and oils, being the triesters of the glycerol, show all the reactions of the simple esters. In the case the glycerides contains the unsaturated fatty acids residues, they also show the usual addition and the oxidation reactions of the alkanes. Some important reactions of the fat and oils are given below. Hydrolysis. Fats and oils are readily hydrolyzed by the treatment with the superheated steam, mineral acids, and the alkalis, and the fat and the oil in the presence of the 500 Kelvin temperature and the pressure, then they give rise to the glycerol and the fatty acids. Hydrolysis by the superheated steam or mineral acids give a mixture of the fatty acids and the glycerol. However, when the hydrolysis is carried out by the alkalis, glycerol and salts of the fatty acids are the formed. Since the salts of the higher fatty acids thus formed are used as a soaps, the alkaline hydrolysis is commonly called the saponification. In the digestive system of the human beings and the animals, fat and oil are hydrolyzed glycerol and the fatty acids by a number of the enzymes called the lipases. Hydrogenation. Oil, which contain a higher proportion of the unsaturated glycerides, add on the hydrogen in the presence of the finely divided nickel as the catalyst to form the solid fat. For example, trioluene, then in the presence of the nickel, give rise to the tristyrene. This process is called hydrogenation or the hardening of the oils. It is similar to the catalytic hydrogenation of the alkalines and the involves the reduction of the double bonds present in the unsaturated glycerides to form the saturated glycerides. This process is extensively used for the manufacture of the vanaspati ghee, such as the dalda, etc., from the groundnut, peanut, sunflower, and the other edible oils. Hydrogenation is never carried out to completion, but it is stopped as soon as the fat of the consistency comparable to ghee is obtained. The completely hydrogenated fats are too hard to be useful as the kitchen shortening. The main advantage of the hydrogenations is that as compared to the oils, fats, hydrogenated oils have better storage qualities and do not become rinsed easily. Hydrogenolysis, conversion to the alcohols, fats and the oils on the treatment with the hydrogen at the high temperature and the pressure and in the presence of the copper chromide as the catalyst undergo the reductive cleavage to form the glycerol and the long chain aliphatic alcohols. This splitting of a fat or the oil to the glycerol and a higher long chain alcohol by the hydrogen is called as the hydrogenolysis. The long chain alcohols thus produced are used for the manufacture of the synthetic detergents. Trans-esterification. Fats and oils can be converted into the simple esters of the carboxylic acid such as the methyl ethyl esters, etc., by the trans-esterification. It involves the treatment of a fat or an oil with a large excess of a suitable alcohol in the presence of acidic or the basic catalysis. The process of the trans-esterification is quite useful for the large-scale preparation of the long-chain fatty acids and the long-chain primary alcohols of the high purity. For this purpose, the mixture of the methyl esters obtained by the trans-esterification is subjected to the fractional distillations to separate the individual esters. These, upon the hydrolysis, yield fatty acids of the high purity. Alternatively, the individual methyl esters are reduced to get the long chain primary alcohol. Addition of the halogens. Like alkenes, unsaturated glycerols and glycerides add the halogens across the double bond to form the addition products. The addition of the iodine is usually carried out by the treating the fat or the oil with the iodine in the presence of mercury chloride as the catalyst. Since the amount of the iodine is used proportional to the number of the double bonds present, therefore this reaction is used for the determination of the extent of unsaturation in a given fat or the oil. Rancidity. When fats and the oils are exposed to warm air and the moisture for a long time, they develop a disagreeable smell and the taste. This process is called as the rancidity and involves the hydrolysis of the esters to produce the fatty acids and the oxidation at the double bonds to form the short chain acids and the aldehydes. These short chain acids and the aldehydes are the volatile and have the offensive smells. Therefore, they impart the unpleasant odors to the oils and fats. Rancidity is the one of the following two types. Hydrolytic rancidity. This type of the rancidity is caused by the liberation of the lower fatty acids by the hydrolysis of the triglycerides. For example, when the butter is exposed to the warm air and the moisture, the hydrolysis of the glycerides in the butter yields butyric acid and the other volatile acids, capric acids with the unpleasant odors. This process of the hydrolysis is catalyzed by the enzyme lipases, which are provided by the microorganisms present in the air. This type of the hydrolytic rancidity can, however, be checked by keeping the butter covered in a refrigerator. Oxidative rancidity. This type of the rancidity is caused by the oxidation of the unsaturated triglycerides by the air to form the short chain acids and the aldehyde having the unpleasant smell. It is believed that the esters linkages are hydrolyzed to yield unsaturated acids which undergoes the oxidation at the site of the double bond to produce the short chain acids and the aldehydes. Oxidative rancidity can be prevented by the addition of the certain chemicals, generally phenols, called the antioxidants. Two antioxidants which occur in the natural fats are the vitamin C and the vitamin E. Analysis of the fats and the oil. Fats and oil are extensively used in the number of the industries. Therefore, it is essential to check the quality of a given fat and oil. This involves the determination of the physical constants such as the melting point, specific gravity, refractive index, and the chemical constants such as the acid value, iodine value, saponification value, rich chert missile value, etc. Some important chemical constants are described below. Acid value. It is defined as the number of the milligrams of the potassium hydroxide required to neutralize the free fatty acids present in the 1 gram of the fat or oil. The acid value is determined by dissolving a known weight of the given fat or the oil in the pure neutral alcohol by titrating against the standard KOH solution using the phenolphthalein as an indicator. The acid value is a measure of the free acids present in a given fat or the oil. A high acid value indicates that the given sample of the fat or oil is quite old and has become the rancid. Saponification value. It is defined as the number of the milligrams of the potassium hydroxides required to completely saponify 1 gram of the fat or the oil. In other words, it represents the amount of the potassium hydroxide in milligram required to neutralize the fatty acids formed as a result of the complete hydrolysis of the 1 gram of the fat or the oil. Saponification value is determined by refluxing a weight quantity 1 to 2 gram of the fat or the oil with the known excess of the standard alcoholic potassium hydroxide solution and then titrating the unreacted alkali against a standard acid. For example, saponification value of the dry rate and the tripalmitin can be determined as the follows. Similarly, for the tripalmitin having the molecular weight this and the saponification is nearly equal to 208. Thus, the saponification value gives an idea about the molecular weight of the fat or the oil. Obviously, smaller the saponification value, higher is the molecular weight. For example, tripalmitin molecular weight 806 has the saponification value of the 208, whereas the trial rate with the molecular weight 638 has the saponification value 263. The saponification value also indicates the length of the carbon chain of the acid moiety present in the oil and the fat. The higher the saponification value, greater the percentage of the short chain fatty acids in the glycerides of the fat and the oil. Butter with the short chain fatty acids has the saponification value between the 210 to 230, whereas the soybean oil has the saponification value between the 189 to 195. Saponification value is used to determine the adulteration of a fat or an oil with the some other oil or the fat with the lower or higher saponification value, or even by the some unsaponifiable matter. Iodine value. It is defined as the number of the grams of the iodine that will combine with the 100 gram of the fat or the oil. Iodine value may be determined by any one of the following two methods. Hubble's method. In this method, a solution of a known weight of the fat or the oil in the tetrachloride CCl4 is allowed to the react with a known excess of a standard solution of the iodine in the ethanol in the presence of the mercury chloride as the catalyst. The unreacted iodine is then determined by the titrating it against the standard sodium thiosulfate solution using the starch as the indicator. For example, the iodine value of the triolane may be calculated as, and this value of the iodine is triolane is 86. Wages methods. In this method, a solution of the more reactive iodine monochloride in the glacial acetic acid is used in the place of the iodine and mercury chloride. A known weight of the oil fat is dissolved in the CHCl3. This solution is then added. ICl added across the double bonds. The ICl left unused is then treated with the Ki solution to liberate an equivalent amount of the iodine. The liberated iodine is then titrated against the standard hypo solution using the starch as the indicator. The amount of the ICl, or an equivalent amount of the iodine that has added across the double bond, is then determined using the following relations. Iodine value V1 minus V2 into N into 12.7 by W. There the V1 is the volume of the hypo used for the blank titration. V2 is the volume of the hypo used for the unreacted ICl and normality of the hypo solution, and W is the weight of the oil and the fat taken. Iodine value is a measure of the extent of the unsaturation present in an oil or fat. Higher the iodine value, more unsaturation is the oil or the fat. For example, iodine value of the linseed oil is 170 to 185, tung oil is 163 to 171, soybean oil is the 127 to 135, sunflower oil is the 140 to 156, olive oil is the 80 to 100. Richard Missile value RM value. It is defined as the number of the milliliters of the 0.1 into normal KOH required to neutralize the steam volatile fatty acids obtained by the complete hydrolysis of the 5 gram of the fat or the oil. To determine the RM value, a known weight of the fat or the oil is completely saponified with the alkali. The resulting solution is acidified with the dilute H2SO4 and then subjected to steam distillation. The distillate, which contains the volatile acid, is then titrated against the 0.1 normal into KH solution. The RM value is then calculated as the follows. RM value is equal to volume of the 0.10 normal KH used for the neutralization into 5 divided by weight of the fat or the oil taken. RM value is a measure of the volatile fatty acids residues present in a given fat or the oil. It is highly useful for testing the purity of the butter and the desi ghee, which contain a relatively high proportion of the glycerides of the butyric acid and the other steam volatile and the residues. The RM value of the adulterated butter is always lower than that of the pure butter. Industrial oils or of the vegetable origin. Drying oils. Certain oils such as the linseed oil, tung oil, china wood oil, perilla oil, etc., when exposed to the air in the thin layer, form the hard and the tough water insoluble solids. This process is known as the drying, and such oils are called the drying oils. Oils like olive oil, groundnut oil, which do not dry or exposure to the air, are called the non-drying oils, and those which dry slowly, such as the cottonseed oil, and are called the semi-drying oil. Chemically drying oil contain a high percentage of the unsaturated glyceride as shown by their high iodine values. On the other hand, non-drying oils have the low iodine value, while the semi-drying oils have the intermediate iodine oil. For example, drying oil have the iodine values above the 150, linseed oil iodine value 170 to 185, non-drying oil have the iodine value less than the 100, olive oil iodine value 80 to 100, while the semi-drying oil have the intermediate iodine value. Cottonseed oil iodine value 105 to 114. Unsaturated glycerides contains the linoleic acids and the linoleic acid as the unsaturated fatty acids residues. These acids contain the 2 and the 3 isolated double bonds respectively. In the general, drying oils containing the unsaturated glycerides with the conjugated double bonds dry more rapidly than those containing the isolated double bonds. Drying oils are used as a medium for the paints, varnishes, and the lacquers. In fact, paints are the suspensions of the some pigments or the organic coloring matter in the linseed oil to which some turpentine oil has been added as a thinner. When these paints are applied on any wood or the iron surface in the thin layers, they quickly dry up to form a tough organic film which protects the surface being painted. Mechanism. The actual process of drying that does not simply involve the removal of the moisture or the evaporation of the solution but involves the complex changes. It is believed that the reactive allylic hydrogens present on the carbon next to the double bonds present in the unsaturated glycerides are first attacked by the oxygen to form the hydroperoxy compounds which then combine with the allylic hydrogen of the other glyceride molecules forming the peroxide bridges. The monomer molecules thus obtained subsequently undergo the polymerizations or to form a tough network solid. The whole process is sketched below. Linoleic acid's residues react with the oxygen, then the hydroperoxides formed, and after that hydroperoxides in polymerization process takes place and the cross-linked polymer are the formed. Soaps. Substances like the soaps and the synthetic detergents which concentrate at the surface of the solution or the interfaces form surface films, residue surface tension of the solution and help in removing the dirt and the dust by the emulsifying grease are called the surface active agents or the surfactants. The molecules of the surfactant contains the two characteristic groups, one of which is the water soluble and the other is the oil soluble. Soaps are the sodium and potassium salts of the higher fatty acids such as the palmitic acids. These soaps are generally obtained by the hydrolysis of the oils and the fats with the aqueous alkalis. The process is called saponification of the oils and the fats. The fats and oils is commonly used for the soap manufacture are tallow, lard, olive oil, linseed oil, rapeseed oil, coconut oil, and the palm oil. Soaps containing the 12 to 18 chain atoms have the good cleansing action. Soaps with the 12 carbon atoms are comparatively soluble in the water, whereas the soaps containing the 18 to 22 carbon atoms are not useful as the soaps because of their insolubility in the water. Sodium soaps are generally hard and hence are called the hard soaps. These are used for washing of the clothes. Potassium soaps, on the other hand, are more expensive and the produce a soft leather and hence are called the soft soaps. These are used for making the shaving cream, shampoos, liquid soaps. Transparent soaps are prepared by dissolving the ordinary soaps in the alcohol and removing the insoluble part by the filtration. Evaporation of the alcohol leaves the behind the transparent mass. Soaps are 100% biodegradable. Microorganisms present in the sewage water can completely oxidize soap into the CO2. As a result, it does not create any pollution problems. However, soap have the two disadvantages. Soap cannot be used in the hard water since the calcium and the magnesium ions present in the water produce the curdly white precipitate of the calcium and magnesium soaps. Soaps cannot be used in the acidic solution since the acids present in the solution precipitate the insoluble free fatty acids which adhere to fabrics and thus block the ability of the soaps to remove the oil and the grease from the fabrics. Synthetic detergents. These days, in the place of the soaps, the substances which are being largely used as the cleansing agents are the synthetic detergents. As the name suggests, they are obtained from the purely synthetic chemicals as compared to the soaps, which are derived from the chemicals which are obtained from the natural sources like fats and oils. In fact, synthetic detergents are the sodium or potassium salts of the long chain alkali hydrogen sulfates or the aryl sulfonic acids. Unlike soaps, synthetic detergents can also be conveniently used even in the hard water. This is due to the reason that calcium and the magnesium salts of the detergents, like their sodium or potassium salts, are also soluble in the water. Hence, synthetic detergents do not form the corrosive white precipitate with the hard water. Further, they can also be used in acidic solution. However, the synthetic detergents have the one disadvantage. Unlike the soaps, they are not completely biodegradable and hence cause the water pollution. Synthetic detergents are of following three types. Anionic detergents. These are so called because a large part of their molecules are the anions. These are of two types. Alkali sulfates. They are obtained from the long chain alcohols by treatment with the concentrated H2SO4 followed by the neutralizations with the NaOH. Some important examples of this type of the detergents are sodium lauryl sulfates and the sodium stearyl sulfate. Sodium lauryl sulfate is also called the sodium dodecyl sulfate (SDS) and is used in the shampoos and the cosmetics. These sodium alkali sulfates are 100% biodegradable. These are also effective in the slightly acidic solutions since they are foam and alkyl hydrogen sulfates, which is a soluble material, whereas the soaps react with the acidic solutions to form the insoluble fatty acids. Alkyl benzene sulfonates. These are obtained by the conversion of the benzene into the long chain alkyl benzene followed by the sulfonation and the neutralization with the NaOH. The most widely used domestic detergent is the sodium benzene sulfonate. Alkyl benzene sulfonates, in which the phenyl group is either attached to the one of the end of the long alkyl chain or any other secondary positions, have the high biodegradable stability and hence are called the soft detergents. While the alkyl benzene sulfonates have the branched chain, alkyl groups have the poor biodegradability and hence are called hard detergents. To differentiate these detergents on the basis of the biodegradability, alkyl benzene sulfonates have the long straight chains such as the sodium para and dodecyl benzene sulfonates, and the sodium 2 dodecyl benzene sulfonate are called the LAS detergents. Linear alkyl sulfonates, while those having the branched chain are called as the ABS detergents. Alkyl benzene sulfonates. Another important example of the ABS detergents is the it is prepared by the Friedel-Crafts reaction of the tetramer of the propylene with the benzene followed by the sulfonation and the neutralizations with the alkali. Cationic detergents. These are the quaternary ammonium salts, chlorides, bromides, acetates containing the one or more the long chain alkyl groups. These are also called the invert soaps because their surface activity is due to the positive ions and not to a negative ions, as in the alkyl hydrogen sulfate detergents. Being the more expensive than the anionic detergents, they find the limited use. Besides being good cleansing agents, they possess the germicidal properties and therefore they are widely used as a germicides in the hospitals. Non-ionic detergents. These are esters of the high molecular mass alcohols obtained by the reaction between the polyethylene and glycol and the stearic acids. These may be obtained from the long chain alcohol by treatment with the excess of the ethylene oxide in the presence of a base. Like the alkyl sulfates, ethoxylates is also the biodegradable. Hydrogen bonding to the numerous oxygen atoms makes the polyether end of the molecule water soluble. Alternatively, the ethoxylates can be converted into the sulfates and used in the form of their sodium salts. Some liquid dishwashing the detergents are of the non-ionic type. Composition of a detergent cake. A cake of the detergents contains about 20% of the active detergent and an equal amount of the sodium sulfate to make up the bulk of the powder. A further 30 to 50% of the sodium polyphosphate or the STPP is the added as an additive. It coordinates with the calcium to positive ions and the magnesium to positive ions present in the hard water and thus enhance the cleansing efficiencies of the detergents. Other integrants like the include the sodium perborate, which acts as the bleaching agent, some optical brightening, or the fluorescence of the compounds which make yellow clothes appear white, and the some foaming agents. Detergent pollution. Detergents having the branched chain hydrocarbon chains cause the pollution in the rivers and the other waterways. The reason being that the side chains stop bacteria from attacking and breaking the chains. This results in the slow degradation of the detergent's molecule, leading to the accumulation. Since the unbranched chain are the more prone to attack by the bacteria, therefore, in the most of the detergents used these days, the branching is kept to a minimum so that the detergent becomes the easily biodegradable and pollution is prevented. The second serious environmental problem is caused by the phosphate additive STPP, which are discharged into the rivers and the lakes from the sewage system. As such, a phosphate is not a pollutant, but it is actually of available oxygen for the fish and the other aquatic animals. As a result of the want of the oxygen, water animals die and rot. In other words, lakes become the full of the dead animals and the vegetation, and hence ceases to act as a source of the potable water. In the view of these environmental hazards, government of the many countries have passed a law to reduce the use of the phosphate additives in the detergent to minimize this source of the pollution. Cleansing action of the soaps and the detergents. All the soaps and the detergents contain the two characteristics group, a water soluble hydrophilic group and an oil soluble lyophilic or the lyophilic group. As a result, one end of the molecule of a soap or the detergent tend to go into the oil phase and the other end to go into the water phase, with the net result that the material soap or the detergent concentrates at the surface of the solution or the interfere. The dirt is generally held to a dirty surface by a thin film of an oil or the grease. When the dirty surface is treated with the soap solutions, the non-polar hydrocarbon chain of the soap or the detergent dissolves in the oil or the grease, and the carboxylate group of the soap or the sulfonate group of the synthetic detergent is held by the surrounding water. This lowers the surface tension between the water and the grease. As a result, a stable emulsion of the dirt in the water is formed. When the surface or the cloth is mechanically scrubbed, the loosened dirt particles are absorbed by the colloidal soap or the detergent particles and ultimately washed away.